Level 1. The Electrical Engineering Student. First, Circuits Lecture. The professor sketches a schematic on the whiteboard, and it looks like something from an archaeology textbook. Resistors, capacitors, inductors, voltage sources, ground symbols. You recognize maybe a third of them from high school physics. Maybe. He starts rattling off Kirchhoff's voltage law and Ohm's law like everyone already knows this. You copy everything down, hoping your notes will decode themselves later. They won't. You're 19, sitting in a 200-seat lecture hall that feels designed to make you feel small. Engineering doesn't ease you in. It drops you in the deep end. Calculus before lunch, physics after, chemistry twice a week, a programming course that expects you to learn C++ in 4 months. You spend more hours lost than not. The lab is where theory collides with reality, and reality doesn't care about your equations. First lab assignment, build a voltage divider on a breadboard. 2 resistors, 1 power supply. The math takes 30 seconds. Getting the thing to actually function takes 3 hours. You wire it backwards twice. You fry a resistor by dumping 9 volts where 3 should go. The smell of burning components becomes part of your week. You buy a multimeter, lose it, buy another one. You start to realize electrical engineering is 10% theory and 90% verifying that things are actually connected properly. Your lab partner builds circuits like he was born doing it. You're still trying to remember which wire color is positive. Red. It's red. You write it on your hand. You'll forget by next Tuesday. Sophomore year, signals and systems. Fourier transforms, Laplace transforms, transfer functions, frequency response. The math turns abstract. You're analyzing signals that don't physically exist to learn principles that supposedly govern everything. Your professor promises it'll click once you take electromagnetics. Electromagnetics makes signals look like child's play. You're deep in Maxwell's equations when it hits you. You don't actually understand what electricity is. You thought you did. You can solve for current. You can calculate voltage drops. But you don't understand what it fundamentally is. And here's the thing. Nobody does. Professors hand you models. Electron flow, field theory, wave propagation. Approximations of something no one has ever directly seen. You're learning to manipulate invisible forces using math that describes things you cannot observe. Junior year. Power systems, generators, transformers, transmission lines, 3-phase circuits. The scale jumps from milliamps to megawatts. You learn the grid is one enormous balancing act, running in real time across thousands of miles. Supply must equal demand every second. Too much and the frequency shifts. Too little and the whole thing cascades. You visit a substation and realize how much of civilization runs on equipment most people will never notice. You also take digital electronics. Computers are just billions of switches flipping on and off at absurd speed. Logic gates, flip-flops, registers, multiplexers. You design a 4-bit adder on paper and suddenly understand how a processor actually works. Not magic. Just an insane number of simple operations stacked together. Senior design project. You and 3 classmates build a solar-powered battery charging system with remote monitoring. You design the circuit, select components, write firmware for the microcontroller, build a prototype. It doesn't work. Weeks of troubleshooting. You find 14 separate issues, fix 13. Presentation day. Panel of professors and industry engineers. The system runs during the demo. Barely. They grill you on design decisions. You answer half with confidence. The other half you admit you haven't fully figured out. They respect the honesty more than the bluffing. You graduate. 4 years of problem sets that consumed entire weekends. 4 years of labs where nothing worked on the first try. 4 years of concepts that felt impossibly abstract. You made it. Families at graduation. They ask what you'll do with the degree. You tell them you got an offer. They ask what the job actually is. You try to explain power distribution engineering. Their eyes glaze over. That's fine. 6 months ago, you wouldn't have understood it either. Level 2, the associate engineer. Day 1 at the utility company. Safety orientation. 4 hours of footage. Arc flash, electrical burns, high voltage hazards, confined space protocols. The instructor puts up photos of real equipment failures, melted copper bus, exploded transformer casings, charred switchgear panels. These aren't textbook warnings. These are things that happen when someone makes a mistake around industrial-scale electricity. They pair you with a senior engineer named Dave, who's been working distribution for 24 years. Dave takes you to a site where crews are swapping out a pole-mounted transformer. You stand back and watch linemen handle equipment carrying 7,200 volts. Dave narrates what's happening. You nod along, understanding about 60% of it. First real assignment. Analyze a feeder circuit for a new shopping center development. The client needs 350 kilowatts. You have to figure out whether the existing infrastructure supports it or needs reinforcement. You open the circuit model in the planning software. Run a load flow study. Voltage drop exceeds limits. The feeder needs upgrades. You draft the engineering report. Dave marks it up. 7 errors. You revise. He finds 5 more. 3 rounds before he signs off. You learn the gap between university and industry. School teaches you how electricity works. Work teaches you the rules. IEEE standards. NEC code. Utility specs. Equipment manufacturer requirements. Everything has a standard. Every standard exists because someone, somewhere, got it wrong and something failed. You follow the rules because they were written by people who paid for the lessons you haven't. 6 months in, your first emergency call-out. A main feeder goes dark. 1,800 customers without power. You drive out with Dave. Fault indicators point to the location. A large limb snapped into a primary line. The recloser tripped and isolated the section. Now you need to reroute power around the damage while line crews clear it. You coordinate with system operators. Switches get thrown remotely. 1,600 customers restored in 35 minutes. The rest wait for physical repairs. You just brought power back to neighborhoods. Refrigerators running. Lights on. Medical equipment functioning. Because you did your job right. That feeling sticks. Level 3, the electrical engineer. 3 years in. The safety net disappears. You get projects without anyone looking over your shoulder. You make decisions that shape how the grid operates. You sign engineering drawings that contractors build from. If your drawing is wrong, it gets built wrong. If it gets built wrong, it might fail. If it fails, people go dark. Sometimes people get hurt. Your first solo substation design. The existing station is 35 years old, end of life for most of the major equipment. You select replacement transformers, breakers, protection relays, SCADA interfaces. You work with vendors on specifications. Create 1-line diagrams, 3-line diagrams, relay coordination studies. You check every calculation, then check them again. Construction begins 5 months later. You're on site every week watching your design become physical. Steel, concrete, copper bus, instrument transformers, all exactly as you specified. Energization day. You're in the control room. Breakers close, relays pick up, telemetry flows. Everything comes online clean. Dave texts you a thumbs up. First substation entirely yours. 25 megawatts of new capacity feeding the fastest growing corridor in the service area. It'll operate for the next 30 plus years. You built something that lasts. But not everything lands. An industrial customer needs a new service connection. You size the transformer based on their load estimate, specify the fusing, complete the design. 2 weeks after energization, the transformer overheats and kicks offline. You pull your calculations apart. The actual load exceeded the customer's estimate, not by a huge margin, but enough to push thermal limits during peak demand. You underrated it. The customer loses half a day of production. The utility eats the cost of a transformer replacement. Your supervisor brings you in, doesn't raise his voice, just asks, "What did you learn?" You learn that customer load projections are always optimistic. You learn to build in margin. You learn that a wrong answer in this field has a $sign attached. Level 4, the senior engineer, 8 years in. You're not just producing work, you're reviewing it. Junior engineers bring you their designs the way you used to bring yours to Dave. You catch their mistakes before they go to construction. You remember making the same ones. They put you on the utility's grid modernization program, a system-wide overhaul, replacing legacy mechanical relays with microprocessor-based protection, installing automated sectionalizing switches, deploying sensors and fiber optic communications for real-time visibility. $45 million over 4 years. You're the lead engineer. You coordinate across a dozen disciplines: protection, telecom, civil, construction, operations, regulatory, environmental. Every design choice ripples outward. You run weekly coordination meetings, track timelines and spend, solve problems that weren't in the scope. A relay vendor discontinues a model mid-project. You qualify a replacement and rework the protection scheme. An underground duct bank floods during construction. You redesign the cable route to keep the schedule. The program finishes on time, under budget. System SIDE drops 28%. Fewer outages, shorter outages. Customers won't notice. They just flip a switch and the lights come on. They only notice when they don't. Your work makes their lives better in ways they'll never register. You start presenting at IEEE conferences. You publish papers on adaptive protection and distribution automation. Other utilities read your work, implement your approaches. You're not just solving your own problems anymore, you're contributing solutions to the field. Level 5, the principal engineer. 13 years in. You're the person people call when the problem doesn't have an obvious answer. When executives need a technical opinion to make a strategic call, your phone rings. You're not managing headcount, you're managing complexity. Less time in the field now, more time running system models, contingency analyses, stability studies, planning scenarios. What happens if this 345 kilovolt line trips during summer peak? Can the remaining circuits carry the load? Where does voltage collapse first? You find the vulnerabilities before they become blackouts. You're also deep in renewable integration. Solar and wind connecting to infrastructure designed decades ago for centralized fossil generation. Renewables are intermittent. The sun sets, the wind dies. The grid still has to stay balanced. You design interconnection schemes, energy storage controls, voltage regulation strategies that keep the system stable through variability. One project, a 120 megawatt solar installation tying into a rural transmission substation. You model the impact: fault current contribution, voltage regulation, protection desensitization, islanding risk. You design the interconnection, specify the inverter settings, coordinate the protection. The farm energizes without a single trip. Clean generation for 35,000 homes. You helped make that real. Level 6, the engineering manager. 16 years in. You move into management. You're no longer just a technical contributor. You lead a group of 18 engineers. Their growth, their output, their careers, that's your responsibility now. Management is harder than engineering. Engineering has correct answers. People don't. One engineer is technically gifted but impossible in meetings. Another is dependable but needs hand-holding on every decision. A third believes they should have your title and resents you for it. You manage all of it while making sure projects ship on time and on budget. Then there's the politics. Budgets get slashed mid-cycle. Projects you spent months scoping get killed because capital got redirected. You deliver the news to your team. You keep morale up when the organization lets them down. You fight for resources in rooms where engineering doesn't have the loudest voice. You protect your people when they make honest mistakes. You hold them accountable when they cut corners. But you also watch them grow. The junior engineer who couldn't run a load flow model 3 years ago is now leading substation projects. The one who struggled with relay coordination is now mentoring others. You built that. That counts for something. Level 7, the Director of Engineering. 21 years in, you run the whole technical organization: distribution, transmission, substations, protection, planning. Over 100 engineers roll up to you. You own the technical direction of the utility. You're in the executive room now. Decisions at this level shape the company for decades. Do we spend $200 million on grid hardening or on generation assets? Do we rebuild aging infrastructure or squeeze 5 more years out of it and absorb the risk? These calls involve hundreds of millions and affect reliability for 1 million customers. You also sit in front of regulators. You testify at rate hearings, justify capital plans, explain why upgrades cost what they cost. Consumer advocates push back. Politicians push back. You defend your position with data, with engineering analysis, with 21 years of experience standing behind every word. Level 8, the Chief Engineer. 26 years in electrical engineering. You're the highest technical authority at the utility. Every major design, every significant standard, every critical technical decision passes through your office. You advise the CEO on technology roadmaps. You set the engineering standards the whole organization designs to. You approve projects worth tens of millions before a single foundation gets poured. You remember being the lost freshman who fried a resistor on a breadboard. You remember not understanding Maxwell's equations and wondering if you belonged. You remember energizing your first substation and being certain you'd missed something fatal. Somewhere right now, a 19-year-old is sitting in a circuits lecture completely overwhelmed. They're wondering whether they're cut out for this. They are. They just can't see it yet. They'll figure it out the same way you did. One burned component, one failed calculation, one late night at a time. They'll learn that electrical engineering means solving problems with forces you cannot see, using models that are never quite perfect. They'll learn the grid is simultaneously fragile and resilient. They'll learn that keeping the lights on is harder than anyone outside this profession will ever understand. They'll build things that last, just like you did. The cycle continues.